constructing classes in Galois cohomology, I mean, of periodic representations. So, I mean, just to remind you, I mean, the idea was, I mean, to use, I mean, certain techniques, cup products and push forwards and so on, I mean, to construct elements in motivic cohomology, and then use a combination of the étale regulator and the Hochschild spectral sequence to get classes in Galois cohomology. So, and we now want to look at a specific example. So, I mean, we want to construct classes. So, I mean, we look at the étale cohomology over Q bar, I mean, of the Shimura variety. So this is our periodic representation. We want to construct a class in the first Galois cohomology group, I mean, over Q, I mean, with values in that periodic representation. Okay, so what do? I mean, we take a motivic class, we take a unit, I mean, on a modular curve. So, I mean, this gives an element in a motivic cohomology group, I mean, of Y1n. And we define Z, I mean, to be the push forward of that unit. So, I mean, that will be an element in the motivic cohomology of our target Shimura variety Y1n squared. Okay, so if we look at the image of this class under the Bailenson regulator and pair it against a certain differential, I mean, coming from two modular forms, I mean, we get this formula, I mean, for this pairing. So, and I mean, I observed that this here is very similar, I mean, to the Rankin-Selberg integral formula. So what we want is to choose a unit such that this formula here precisely gives the Rankin-Selberg integral formula, okay? So we make the following observation. I mean, what do we need? So for star, so for the Rankin-Selberg integral formula to be the image, so be the image, so under the balance of a motivic class, so under the Bailenson regulator. So what do we need? We need to find a unit. So a unit U. So it's a unit on Y1n. So where we allow denominator, so we tensor with Q. So such that the logarithm, so of the absolute value of U is equal to E0 1 over n. Okay. So I mean, if we can do that, I mean, then our motivic class here, I mean, will have a relation to values of L functions. And that is a good sign, I mean, that this class, I mean, can be extended to an Euler system, or its image in étale cohomology can be extended to an Euler system. Okay, so I mean, let me call this here, I mean, double star. Now it turns out by miracle there is such a unit, and it's called a Siegel unit. So in fact, so such a unit exists. Such a unit exists, so it's called the Siegel unit. Siegel unit. So which, I mean, is generally noted by G1 over n, so it is a unit, I mean, on Y1n. So, and this relation here, so one can prove this relation is Kroneker's second limit formula. So, and so the relation double star is Kroneker's second limit formula. Okay, so I just want to remark, I mean, that so these units are really miraculous objects. Yeah, I mean, so for example, so one can show, so also if one computes, I mean, the D log of this unit, of the Siegel unit, so then this is E2, so 1 over n, so which is a weight 2 as the side series. So in some sense, one should think of Siegel units as cohomological incarnations of GL2 Eisenstein series. Yeah, and it turns out, I mean, that Siegel units are basically the building blocks for all the Euler systems we know so far. Well, that was true until recently. So, I mean, well, I will explain a little bit more about that later, but I mean, the problem, or one of the obstacles sort of for constructing Euler systems in huge generality was the lack of an analog of Siegel units for other kinds of Eisenstein series. I mean, you could, for example, look at Eisenstein series, I mean, for the symplectic groups, yeah, or for GLN, or for whatever. The question is, I mean, is there a motivic incarnation of that? And the answer was, we didn't know. Yeah, I mean, now Chris Skinner and one of his students succeeded in constructing analogs of Siegel units for the symplectic groups. And that will give rise, I mean, to many new Euler systems. But so far, we really were limited to this case. We were limited, I mean, to choosing our units to always be Siegel units.
So their construct,
sorry?
So their construction is for any genus? Or
sorry?
Their construction is for any genus?
What do you mean for any genus?
You said the symplectic group, so GSP or GSP6 or?
I think so. I think they can. I think they've written it up for or are writing it up for GSP4, but I think their construction works more generally.
Do they use Eisenstein series for that as well?
Yes, I mean, these will again be cohomological incarnation of Eisenstein series. So if you compute the image of the units, I mean, under the Balian regulator, you will again recover Eisenstein series for GSP4.
Okay.
So it's some higher genus analog of this chronicle liquid?
Yes, I guess. I mean, I haven't seen their preprint yet. I mean, they announced that recently, but I mean, yeah, but I mean, it was a construction which for many years, I mean, no one knew how to do. So, okay. Well, in any case, so what can we do with that now? So definition. So definition, I mean, we let Z1, so let curly Z1 be the push forward, I mean, under our diagonal embedding of the Siegel unit. So, I mean, where does this live? I mean, this here is an element of the H3 motivic of Y1n squared with coefficients in Q twist 2. So, I mean, that just comes from the properties of push forward maps in motivic cohomology, where you have the shift, I mean, in degrees and twists. So, this here, I mean, we call the Balancen Flach element. Balancen, so Flach element. So then, so we look, I mean, at this class, at the image of this class under the Balancen regulator. So, and we pair it against our differential. So then this will just be so some explicit non-zero factor, so times L prime of Fg. So at right. So here, so I remind you, I mean, that W was F of minus tau bar, G of tau, so D tau wedge D tau bar. So I want to make a comment here. So this here lies in the middle one, I mean, of the de Rham cohomology of a modular curve. So, I mean, this here is neither holomorphic nor anti-holomorphic, right? I mean, it has an anti-holomorphic component and a holomorphic component. I mean, this will be important later, I mean, when we look at generalizations of this. Okay, so what is now, we now make the following definition. I mean, I want to now specify a certain periodic representation. So, okay, so we let VP of F, so is the largest so of our étale cohomology groups of the H1 étale, so Y1n base change to Q bar, QP. So on which all the Hecker operators act, I mean, by eigenvalues, I mean, of F. Okay, so on which, so the Hecker operators operators TL. So for L not dividing N. So act as, good morning. So act as so a L of F. Okay. So then we can, so this here, this is actually a periodic, so this is a direct summand of this periodic representation. And it has the following properties. So VP of F is two-dimensional. VP of F is two-dimensional. So, and VP of F star, so is a subspace or direct summand, I mean, of the H1 et al. So of Y1n Q bar QP is 1, because there's a certain kind of self-duality, I mean, of the VP of F. Okay, so what do we get from this? So if we look at the representation V, which is VP of F, start as VP of G star. So that this is a direct summand, So of the H2 et al. Of Y1n squared, base change bar QP twist 2. So, I mean, this is just an easy application of the König formula. Right. I mean, I came out that we can construct from our class Univalenzen flache element, a class in the first Galois cohomology group of this representation V. So here's the definition. So we let Z1 so be the image of curly Z1. So under the following composition of maps. Okay, what is this composition of maps? So, I mean, we start, so I mean, our class curly Z1 starts its life in the H3 motivic, so of Y1n squared, so Q twist 2. So, and now we just apply, I mean, this formalism we examined yesterday. So we look at the image under the et al. Regulator. So this brings us into the H3 et al. Of Y1 n squared with coefficients in QP twist 2. So then we use the Hochschild spectral sequence. So to bring us into the H1 of Q with values in the H2 et al. Of Y1n squared, Q bar, QP twist 2. Okay, and now we use, I mean, that V is a direct summand of this. So we just project into the direct summand, so to get a class with values in. Okay, so there we go. So we now start with our class curly Z1 in here. And we define Z1 to be the image of this class under the of maps. Okay, so this is the bottom class of our Euler system. Right. So let me just make some remarks. So, I mean, firstly, so we should think of the class Z1, so as a cohomological, so as a cohomological incarnation. So of the Rankin-Selberg integral formula. That's probably more true for this class. That one. As a cohomological incarnation of the Rankin-Selberg integral formula. Because precisely the in some sense, I mean, the same ingredients are there in the Rankin-Selberg integral formula as there are in the construction of this class. I mean, this class is constructed using this push-forward map from y1n into y1n squared. And one can interpret the Rankin-Selberg integral formula so that we take a differential, I mean, on y1n squared, I mean, coming from f and g, put it back along this embedding iota, and then pair it against an Eisenstein series. So the ingredients, I mean, in the integral formula and in the Euler system or the construction of this class, I mean, are precisely the same. So, and then, I mean, so the second remark is, so we know, so from the computation, so of the class Z1 under the Balancian regulator, that Z1 is non-zero. Because I mean the value of the Rankin-Selberg F function at 1 is non-zero. So it follows that Z1 is not zero. But what about this class in the Galois homology? R et al. Is not known to be injective. Be injective. So we do not know. Well, at least we don't know without much further work. I mean, whether Z1 is not equal to zero. Yeah. I mean, this is a very hard problem. I mean, this precisely, I mean, I hinted at yesterday. So that if we have an Euler system, or in this case, I mean, the bottom class of an Euler system, it is a really hard problem. I mean, to try to give a criteria when the bottom class of the Euler system is non-zero. I mean, one can do this. I mean, so in this case, I mean, that was done by Bertolini, Darmon, and Roger. But these are some very delicate computations in symptomic cohomology. Yeah, so in some sense, one replaces the Balancian regulator by the symptomic regulator, which compares directly into étale cohomology. And then one wants to prove, I mean, an analog, periodic analog, I mean, of the Rankin-Selberg integral formula. But I don't want to go into that. I mean, so let me just sort of say, I mean, this is hard. So, and that was proven in this case by Bertolini, Darmon, and Roger. That's correct.
How does one?
I guess, I mean, that is classic. One can probably just write down, I mean, what this derivative is. It's classical Rankin-Selberg theory.
If you don't take Rankin-Selberg, if you just take L prime of F, then it could be, I mean, if it's rank 3, then it vanishes, right?
That's true. Well, maybe it can vanish, but at least you have a criterion for checking, I mean, whether the class is non-zero.
Also, you have to go through all these steps to show Z1 is not zero in the cohomology.
Yeah.
And then together L prime is not zero.
No, I mean, it works the other way around. I mean, you have no way of knowing whether your cohomology class is non-zero. You use the properties, I mean, of the L function to deduce that your cohomology class is non-zero.
But a priori, your F and G are fixed.
Well, F and G you can choose. I mean, so.
But can you choose F and G so that this L prime is actually zero?
Well, you could, I guess, yeah.
Okay.
I'm not sure, I mean, which modular forms you can, I mean, the F and G just determine, I mean, which differential, I mean, you pair against, right?
Okay. So,
I mean, you're free to choose F and G.
So you choose F and G, so L prime FG is not zero.
Yeah.
Okay.
Yeah. Sorry, I should have made that clear. Right, so then this the third question, so that the question, so is Z1 part of an Euler system? Well, okay, because that is not obvious. I mean, we have constructed, I mean, this one class in the Galois cohomology of Q, but as I said yesterday, I mean, an Euler system is an infinite collection of classes defined over all the cyclotomic extensions of Q. Yeah, so the answer is yes. I mean, it is part of an Euler system, and I'll explain to you how we construct the other classes. So this is the Valence and Flach Euler system. The Valence and Flach, so Euler system. So how do we construct the other classes? So we need to look, I mean, at modular curves, I mean, of higher level. So we define, so for m greater or equal to 1, so we let Zm be equal to y1 of m squared n. Okay, so then I can show the proposition. So there exists a finite map. There exists a finite map, so which I will call iota m. So from Zm, so into y1 of n squared, which only which corresponds, so on the upper half plane, so corresponding to Tor maps to Tor and Tor plus 1 over m, so on the upper half plane. Okay. So that is a finite morphism. And one can show that it isn't defined over Q, but over Q adjoins the mth roots of unity. Okay, so this is defined. So iota m is defined, so over Q adjoined mu m. Okay, so I mean, you can probably guess how we will proceed now. So we take a Siegel unit on Zm and push it forward, I mean, under this slightly twisted embedding, I mean, into the motivic cohomology of y1 n squared. So definition, so we let Zm is the push forward under iota m of a Siegel unit, m squared, g1 over m squared n. So where does this live? So this lives in the H3 motivic of y1 n squared, base change to Q adjoint mu m, with values in Q twist 2. Okay. So, and if we then again apply the étale regulator as the Hochschild-Serre spectral sequence, so then we get a class, I mean, Zm, which lives in the H1 of Q adjoint mu m. So this values in, okay. So the key really is, I mean, to define this finite morphism, so which is defined over the m cyclotomic field, but doesn't descend to Q. So in this way, so we get a collection, so of classes, I mean, Zm for m greater or equal to 1. Okay. Question, does it satisfy the Euler system norm relations? Because you remember, I mean, that we in Euler system, if we compare the classes, I mean, their behavior should be governed by the local Euler factors in the product expansion of the L function. So question, so is it an Euler system? So, I mean, the answer is yes. So, okay, so there are two proofs of that. So there is one proof, which, so that's joint work with David and Antonio Ley. So where we give a proof by bare hands. So in other words, I mean, so the construction of these classes, I mean, is quite explicit, right? I mean, you take a Siegel unit, you have this nice map, iota m, I mean, you push forward the Siegel unit. So, and then by messing around, I mean, with these modular curves, we give an explicit down to earth proof, I mean, that they really satisfy the norm relations. That is 35 pages of really tedious computation. Okay, so don't read it. So here's a proof. So proof by bare hands. So which is not recommended. I mean, it is already not recommended because we later want to construct Euler systems. I mean, for much more complicated Shimura varieties, where we don't work with modular curves, but maybe with Siegel three-folds or Picard modular surfaces. So our Euler factors, I mean, become, I don't know, I mean, polynomials of degree 4 or degree 6 or degree 8. So you can imagine if you try and prove norm relations by bare hands, it's simply not going to happen. Yeah, so we needed a more intelligent way, I mean, of proving this. So, and there is a more intelligent way, I mean, which we developed, I mean, for an Euler system for a symplectic group, and which my student Giada Grossi then gave a new proof of the norm relations in this case. So Grossi is a proof. So a proof, I mean, via smooth representation theory. So, I mean, this proof is way shorter. I think it's 2 or 3 pages. So, and it is clearly the conceptually right way, I mean, of proving these relations, because this proof, I mean, generalizes. Okay, so and let me just make a remark. So, I mean, I talked here, I mean, about the Rankin-Selberg integral formula where f and g are modular forms of weight 2. There is a construction, I mean, there is an analogous construction when f and g, I mean, are higher weights. And in this case, you have to work with motivic cohomology with coefficients. Okay, so it becomes a little bit more complicated, I mean, keeping track of the coefficients, but essentially the idea is the same. So we have, together with Kings, David and I constructed an Euler system. So Euler system. So for f and g of weight, so greater than 2, greater or equal to 2. So this involves some motivic cohomology, so with coefficients. But I mean, the idea is already there, I mean, in the case when f and g are weight 2. Okay, so what do we learn from this? So let us now sort of try and extract, I mean, from this construction, the general ideas, I mean, for constructing an Euler system. So a general strategy. So we start with a Rankin-Selberg type integral formula with a Rankin, so the Selberg type integral formula. So for an L function, attached to an automorphic form, So we try and recognize that as the Bailenson regulator. So try and recognize so this integral formula. So as the Bailenson regulator, well, as the image so of some motivic cohomology class, so under the Bailenson regulator, Bailenson So regulator, and then we look at the image, I mean, of this motivic cohomology class in étale cohomology. So look at image, so of the motivic class, so under the étale regulator. So, well, under R étale. So, and I mean, this then should be, I mean, the building block for an Euler system. So, building block, so block, so of an Euler system. Right, well, this is a nice strategy. I mean, there's certainly lots of Rankin-Selberg type integral formulae, but as I said before, I mean, there are certain restrictions. Yeah, I mean, one can't always, I mean, carry that out. So remark. So some remarks, so this doesn't always work. This doesn't always work. So for the following reasons. So firstly, many Rankin-Selberg type integral formula do not involve, do not involve groups which have Shimura varieties. Many Rankin-Selberg type integral formulae so involve groups so which do not have Shimura varieties. So Shimura, so varieties. So for example, e.g., so GLM times GLN, where M and N is not equal to 2, so Mn is not equal so to 2. And then, as I said before, there is no useful generalization of Siegel units, or well, there wasn't, I mean, so no, so generalization of Siegel units to higher groups. Well, as I said, I mean, that may well change now with the work of Skinner and San Giovanni. But I mean, so far we were restricted, I mean, to any integral formulae where the only Eisenstein series occurring were those that were coming from GL2. I mean, luckily there are quite a lot of those. So, I mean, I want to look at an example in a moment. I mean, so let's look at an example. Namely, if we look at the spin representation attached to a genus 2 Siegel modular form. I mean, there's a very nice integral formula, I mean, which again involves GL2 Eisenstein series. And I want to explain now, I mean, how is this, what happens if we try and follow this strategy. Okay. So, yeah, so well, let me just sort of write down this remark. So hence, we restrict, so to integral formulae, so involving so GL2 Eisenstein series. Okay, so here's an example. So which is an Euler system. So an Euler system, so attached to so the spin representation of genus 2 Siegel modular forms. genus 2 Siegel modular forms. Wow, time flies. Well, okay. Right, so the setup is the following. So definitions. So let me fix, my conventions for the symplectic group. So I will let GSP4. So it's a subgroup of GL4. So these are symplectic matrices. Symplectic matrices. So with respect to the matrix. So I take the anti-diagonal 1, 1, -1, -1. Okay. So this X, so this is our analog of GL2. So we need an analog, of the upper half plane. So this is the Siegel upper half space. So we define H2, to be the set of Z. So these are 2 by 2 matrices. So where Z is symmetric. So, and the imaginary part of Z is greater than 0. So, and then so this has an action of GSP4 of R. So we have an action here, so of GSP4 of R. So, and one can then define, what a genus 2 Siegel modular form is. So, these are certain functions, from H2 into the complex numbers, which satisfy certain transformation properties under the action of this group. This is all quite analogous, to the definition of modular forms. So a genus 2, so Siegel modular form, so of parallel weight 3. So, is a holomorphic function, so from H2 into C. So with certain transformation properties, transformation properties, so under the action of SP4 of Z. Okay. So, well, of course, you can also define, Siegel modular forms, of weights, bigger or different from 3. So remark. So we can define. Siegel modular forms. So of weights, so K1, K2, so where K1 is greater or equal to K2. So, and it turns out when K1 is strictly bigger than K2, then these Siegel modular forms are vector valued rather than scalar valued. So these will be vector valued. So if K1 is strictly bigger than K2, so, and there exists a notion of a cuspidal eigenform. A notion of a cuspidal eigenform. Okay, so all of the theory, from that we know from modular forms, generalizes very nicely. So, and we let F, so we let curly F, be such a cuspidal eigenform. Okay. Right. So I now want to explain this integral formula. So we need to talk about differentials attached to such a genus 2 Siegel modular form. So let us briefly just recall, what we saw in the case of regular, elliptic modular forms. So if F is a weight 2, so elliptic modular form, So then we have two differentials on y1 of n attached to f, namely a holomorphic one and an anti-holomorphic one. Okay, so we have two differentials so attached to f. So to f, so on the modular curve y1n, namely we had the holomorphic one, so which is f of tau d tau. So, and we have an anti-holomorphic one, so which is f of minus tau bar, so d tau bar. So what characterizes these two differentials is that they have the same Hecke eigenvalues. Same, so Hecke eigenvalues, so as our form f, okay? So that means these differentials, did turn up, in the Rankin-Selberg integral formula. So we need to understand, what happens, so what kind of differentials are attached to such a cuspidal Siegel modular eigenform, okay? So it turns out that there are 4 of them. So nice to write on clean blackboards. Right? Right, okay, so what is the situation? For Siegel modular forms. So if f is a weight 3,3, so genus 2 Siegel modular form, genus 2, so Siegel modular form, then there are 4 differentials. 4 differentials. So on a Siegel threefold, which I will call S, so which is a Shimura variety, so for the group GSP4. So with the same Hecke eigenvalues as F. Where is the same? So Hecke eigenvalues, so as F. So we have, so which I will call eta 0, which is holomorphic. So then we have eta 3, which is anti-holomorphic. So far, this is precisely the same picture, as for the usual modular forms. But then we also have 2, which are a bit awkward, which are neither holomorphic nor anti-holomorphic. So we have eta 1 and eta 2, so they are neither. Okay, so what do we say here in terms of de Rham cohomology? So in terms of de Rham cohomology, so we have, so if we look at the H3 de Rham, so of S over C, so this will, we have the splitting, of the Hodge filtration. So we get 4 terms, so from I equal to 0 to 3 of the H3 minus I of SC with coefficients in omega I. So this is just the Hodge splitting. So, and then this the class, so of eta I, so will lie in the H3 minus I of SC, this values in omega I. Okay, so in other words, I mean, so we have the two extremal parts. I mean, when I is 3 or when I is 0. So this is where the holomorphic and the anti-holomorphic differentials live. And then we have these two intermediate parts. So, I mean, where these two rather awkward fellows live. Okay, so what does this have to do with integral formulae? So attached to our class F, I mean, we can look at an L function. So L spin, so of Fs. So this is the spin L function. Spin L function, so of F. So here, I mean, the local factors are polynomials of degree 4. So the Euler factors, so are polys, so of degree 4. So, and then for these 4 values of this L function, we have the following integral formula, which is due to Piatetsky-Shapiro. Piatetsky-Shapiro integral formula. Okay, so what is this? So we look at the following embedding. So there exists an embedding. So iota from the product of two modular curves into our Siegel threefolds, which is induced by the following map of groups. Induced by, so the map of groups, so from GL2 times GL2 into GSP4. So which is explicitly given as follows. So if I have two matrices here, A, B, C, D, and A prime, B prime, C prime, D prime. So then this maps to the 4x4 matrix. So A, B, C, D, A prime, B prime, C prime, D prime. Okay, so you can check, I mean, that you really get a symplectic matrix here. Okay, so what is the integral formula? So L spin, so of F, so at the value -1/2 is given by, well, some explicit non-zero factor. So we integrate, so over the C points of the product of two modular curves. And what do we integrate? E1 times E2 times the pullback under this embedding iota of our differential eta 1. Okay. So, and E1 and E2 are suitable GL2 Eisenstein series. E2 are suitable GL2 Eisenstein series. Okay. So, I mean, this looks quite promising, right? Because we have an integral formula which is built up from GL2 Eisenstein series. So looking at this formula gives us a clue how we can realize this. I mean, as the image under the Bailenson regulator under a motivic class. Namely, so what are the ingredients here? So we look at this embedding of two modular curves into the Siegel threefold. This will induce a map on motivic a push forward map under motivic cohomology. And the idea is, so we want to have two Siegel units, because in the integral formula, I mean, we have two GL2 Eisenstein series. So the idea is to construct a motivic cohomology class. We take two Siegel units, I mean, on the product of two modular curves, and push them forward along this embedding iota to get a class in the motivic cohomology of the Siegel threefold. Yeah. So let's see what happens when we do this. So the idea. So the idea, so we let G1 and G2, let G1 and G2, so in O of Y times tensor Q be Siegel units. So be Siegel units. So such that, so the logarithm log, so of GI is equal to our Eisenstein GL2 Eisenstein series EI. So then we remember that this here is an element. I mean, this here is just the group H1 motivic of Y with coefficients in Q twist 1. So in other words, if we look at the exterior cup product of G1 and G2, so this will be an element in the H2 motivic, so of Y times Y with coefficients in Q twist 2. And now we push this forward under our embedding. So we now define, so we consider the push forward of this. So which will be an element in the H4 motivic, so of S with coefficients in Q twist 3. So I mean this class, I mean we call the lemma-flach element. Lemma-flach element. So lemma, because Francesco Lemma, I mean, was the first one who studied this class. And what he showed is, so we have the following theorem. So Francesco Lemma. So that if we now take this class here and we look at its image under the Bailenson regulator, so RB of the push forward of G1 and G2, so and we pair this against the class so eta1, then this is up to an explicit non-zero factor, precisely the Piatetsky-Shapiro integral formula. So if you get E1, E2, so times the pullback of eta1. Okay. So, I mean, I hope I've sort of made it clear, I mean, how we got, I mean, to this motivic cohomology class. Namely, we looked at this integral formula. Yeah, I mean, so we want to sort of interpret this, I mean, in motivic cohomology. So, I mean, these two Eisenstein series come from Siegel units. And here, I mean, we have this embedding iota. So the idea would be, I mean, to take the Siegel units and push them forward, I mean, under the under iota. Yeah. So, and I mean, this is clearly a strategy, I mean, that one can carry out. I mean, whenever you have an integral formula, I mean, involving some GL2 Eisenstein series. Okay. Let me maybe just say about the theorem. I mean, this is actually a rather delicate computation because the boundary of a Siegel threefold is really complicated. So it is not as simple, I mean, as in the Rankin-Selberg case. Okay. So well, we have the theorem. So this means, so that's this class, which I'll again call Z1, which is this push forward of G1, cup G2. So it's a promising candidate, candidate so for building an Euler system. Okay. So what is the periodic representation in question? So step 2. So we consider the image of this class under the étale regulator. So which is an element of the H4 étale, so of S with coefficients in QP twist 3. So in order to now apply the Hochschild spectral sequence to go into Galois cohomology, we need to know that this is homologically trivial. But it turns out, I mean, so this is homologically trivial. So after localization, so at the maximal ideal, so of the Hecke algebra, so algebra corresponding to F, to F. And then Weissauer has shown the following theorem. So F gives rise, so to a four-dimensional Galois representation, four-dimensional p-adic, so representation, so which I will call V spin F. So, and if F is non-endoscopic, so if F is not a lift, so from smaller groups, so then there exists a projection map. Then there exists a projection, so from the H3 et al., so of S space change to Q bar with coefficients in QP twist 3. So onto, say, so V, which is VP spin, by V spin F dual. Okay. So, I mean, this is again, I mean, as we saw it in the Rankine-Selberg case, I mean, that the p-adic representation attached to a pair of modular forms is a direct summand of the H2 et al. Of the product of two modular curves. So, I mean, this is the analog, I mean, of this result. So, and then we have step 3. So, step 3, so we let Z1 be the image under the following map, or the following composition of maps. So, we start with a class here. Then after localization at our maximal ideal, this gives a class in the H1Q, so H3 et al., so of SQ bar, QP twist 3. And now I'm running out of space. So, and this here then maps via this projection into the Galois cohomology of V. Okay. So here we have this class, so the image under the et al. Regulator of our class Z1. And we get a class here in the Galois cohomology of V. Okay, so question, I mean, is this an Euler, is this a bottom class of an Euler system? Well, it turns out the answer to this is yes. So here's a theorem, so which was joint work with David and Skinner. So theorem, so Löffler, Skinner, so myself, Skinner. So under suitable, so under some suitable ordinarity assumptions. So assumptions So Z1 is the bottom class of an Euler systems. So Z1 is, so extends so to an Euler system. So for the representation V. So, I mean, the idea is again, I mean, to sort of look at higher level modular curves, I mean, to change the embedding very slightly. Again, I mean, using translation, I mean, by 1 over m. So you get a morphism defined over QP, over Q adjoins the mth roots of unity, and then push forward, I mean, Siegel units from this higher level modular curves, I mean, into the Siegel threefold. Yeah, so that's how you get classes over the cyclotomic extensions. But then, I mean, you need to prove the norm relations. And this is, I mean, where we knew we had to develop a different strategy for proving norm relations. Because, I mean, trying to prove, so the Euler factors, I mean, are polynomials of degree 4, and it simply wasn't feasible, I mean, to do that by bare hands. And then we had this idea, I mean, of using smooth representation theory, I mean, where it just very naturally comes out. Okay. So then there is again the question, so theorem, so this is joint work with David. So we needed a criterion so for the bottom class of this Euler system to be non-zero. So again, for the motivic class, you get a criterion from the Piasecki-Shapiro integral formula, right? But here, I mean, again, one doesn't know, I mean, that the étale regulator is injective. So proving, I mean, that this class in Galois cohomology is non-zero is very, very difficult. And I mean, we were, in fact, I mean, stuck on this for about 4 years. So, I mean, that was there, as I had mentioned in my lecture in December, the breakthrough came, I mean, when we heard Piloni's talk in Princeton. And then it was instantly clear, I mean, that was the that was the missing piece, I mean, for these computations. So this here is hard. So, I mean, if you're interested, I mean, in how one does that, I mean, that was part of the lecture series which I gave at MSRI a few months ago. So, I mean, the videos of that are online. Okay, so, I mean, let me finish, I mean, with the following remark. So, I mean, there are many other examples. So there are many other examples. So of constructions of this type. So of constructions of this type. So for example, so we can construct an Euler system. So for the Assay representation, so of a quadratic Hilbert modular form. So, I mean, this was first done, I mean, together with David and Antonio Ley. So, and then generalized, I mean, well, we proved it under certain assumptions, I mean, on the real quadratic field. And I mean, that assumption was then removed by my student, Giada Grossi. So, and here the integral formula is Assay's integral formula. Starting from, so Assay's, so integral formula. So, I mean, for this integral formula, so, well, okay, so I mean, just sort of in a nutshell. So, I mean, if we write, so curly y, I mean, for our Hilbert modular surface, so then one is a natural embedding, I mean, of a modular curve into the Hilbert modular surface. So let us call this iota. So, I mean, if we have then curly f, I mean, our Hilbert modular form of weight, so 2, 2, I mean, this, then we have an Assay L function of f. So, and I mean, what this integral formula says is that a certain value, I mean, of the Assay L function, or I think the derivative at f equals 1, So is the integral, I mean, over the C points of Y, so of a certain Eisenstein series, a GL2 Eisenstein series, times the pullback under iota of a certain differential attached to F. And I mean, again, this differential is neither holomorphic nor anti-holomorphic, but something in between. Okay. So you can probably guess now how we construct our motivic cohomology class in this setting. So here is one Eisenstein series for GL2. We take a Siegel unit and we push it forward under this embedding, and that's it. Okay. So, okay. I mean, I hope I've given you an idea. I mean, where one starts looking for Euler systems, and I mean, a general strategy. I mean, how one can then construct them. Thank you.